on block day we found the area of that thing, top minus bottom, left to right. Today we're going to, out of that area, we're going to build out of the page, coming up out of the page or out of the screen, either squares or triangles or semicircles, usually just one of those because anything else is kind of crazy. There's equilateral triangles there. But visualizing it is kind of the hard part. So I was looking earlier, some of you saw me looking for pictures. This is a popular project to make calculus students do. You can kind of see, this one won't blow up, I don't know why. You can kind of see what the base was, and then coming up out of the base, this one has semicircles, that one looks like some kind of rectangle, that one looks like squares, and I think that one's triangles. They all had the same base, but different shapes coming out of the base. Does that make sense? Can you see what we're headed toward? Like, the visualizing is sometimes the hardest part. I was looking for pictures. There's a decent one. So there's the base area right there, and then building up out of that base, coming out of the page, it looks like they're squares. So the job today is to find the volume of those weird pieces, or those weird shapes. I didn't see too many other good ones. There's one where the cross sections are semicircles. Yeah, some of the others are harder to see. Some people have ease, like can draw them well, and others struggle drawing. So I hope the pictures helped visualize what we're going to do today. All right, consider region R on the right. This region is the base of a solid coming up out of the page. So we're like looking top down on this, and in a minute we're going to build some things coming up out of the page of this. For this solid, we know the shape of every cross section perpendicular to the x-axis. So our cross sections are going to be perpendicular to the x-axis. That's nice because that means it will be a dx problem. If they're perpendicular to the x-axis. If they're perpendicular to the y, well then you got to do the dy problem. The cross sections might be squares, might be triangles, might be semicircles, could be anything, but usually we're sticking with the basic shapes that we know the areas of. Some are smaller than others. Let's try to sketch in what a square cross section would look like. This is where things get a little bit hairy. So there's the distance from top to bottom. So I want a square coming up out of the page, and so you have to like figure out how to draw coming out of the page a small square, as opposed to way over here, that's going to be a much larger square coming up out of the page. And then again, way over here, you'd have a really small square coming up out of the page. Yes, no, give me a 1 to 5. How are you on visualizing what that thing looks like? Show me like 5, like I can picture it perfectly in my head. 3 is like, I got an idea. 1 is like, I have no idea what's going on. Okay. Mostly 3s, 4s, and 5s. Again, these pictures may help more because those are like professionally done. But you're going to be stuck doing some on your own where you'll have to draw. Well, you don't have to draw, but I think it helps to solve the problem. Each cross section is going to have the same shape. We're never going to like mix it up and be like, oh, half of it's squares and half of it's semicircles. Here's some more visual representations. So there's square cross sections. I don't know why it doesn't just say square cross sections right there. Equilateral triangle cross sections, semicircle cross sections, and so on. The crucial formula to remember for all volumes, let's see if we come up with it here. Let's look at that one slice that we drew earlier. The trick is that slice has a thickness. Do you know how thick that slice is? It's similar to the thickness of the rectangle from yesterday. So you know how thick that slice is? Dx. So the thickness of that slice is dx. The area, or the area of one of the squares, would just be s squared. And so that total, the volume of that piece would be, the volume of that piece would be the area of the piece times dx. The area of the piece times dx. Does that make sense? Good old volume formula, like area of the base times the height. That's what that is. Capital B times H, the old tax formula chart. The area of the base times the height. It's just that our height is like really small. It's a dx. And then what we want to do is add up all of those little volumes from wherever, A to B. So there's our big S. Add up I'm going to say add up all the volume pieces. First of all, that's not our equation, but that's sort of how we think of it. We're going to add up all the pieces from A to B. But the pieces are the area of a cross-section times its thickness is dx. So that's the formula, but I don't know that it's a memorized formula. It's like yesterday we added up all the little rectangles. Today we're going to add up all the little volumes. Well, maybe this is obvious, but we'll need to know formulas for the areas of basic shapes in terms of S, one side, the side that's in the length. We almost always call that length S. Okay, S is either the vertical distance, top minus bottom. So there's that top minus bottom thing again. If it's the horizontal distance, then it's right minus left. And like yesterday, we prefer dx problems, but sometimes we get stuck doing dy problems. So a rectangle would be base times height, but in terms of S would be the base, the height would have to be given. And sometimes it'll just tell you rectangles with a height of 2 or rectangles with a height of 1. Area of a square, S squared. Equilateral triangle, maybe you've seen this before, maybe not. We could derive it if we really wanted to. But you probably just want to trust me because you're going to memorize this one anyway. Root 3 over 4s squared. To me, that's the only one that I memorized because the others I can figure out. A semicircle is, let's see, 1/2 pi r squared. But we have to be careful. We don't have r, we have s, and s is the diameter. So it's 1/2 s over 2 squared. I don't memorize that one. I know the area of a circle, so I can figure that one out. Some people do memorize that one, and if you're going to memorize it, you figure out that 2 squared is 4 times 2 is 8. And so if you want to memorize it, it's pi over 8 s squared. I don't ever memorize it, so you won't ever see me use that formula. I will just go back to, I know what the area of a circle is, so I know what half the area of a circle is. I will use that. Most of these are calculator problems anyway, So it doesn't matter about simplifying, like the calculator is going to do all that anyway. So if you want to memorize, it's pi over 8 s squared. If you want to remember the area of a circle, then you can just figure it out every time. Isosceles right triangle with a leg on the base. So that means it would look like this. This is another one that I'm not going to memorize. What's the area of that triangle? What's the area of any triangle?
1/2 base times height.
1/2 base times height. So 1/2 base times height, 1/2 s squared. Again, I'm not coloring that one orange because I don't need to memorize that. I know what the area of a triangle is. If you don't know the area of a triangle, well then maybe you need to memorize that. Isosceles right triangle. So same shape, except now the hypotenuse is on the base. So there's S, but instead of S being a side length, S is a hypotenuse. That's an S. It's another one that I don't memorize because I can... Here's how I figure it out. So S squared would be a square, and I want 1/4 of it. So 1/4 s squared. I don't memorize that. So in my mind, there's one thing that I have to memorize. Even then, I could go through to figure that out, but that one you got to memorize. The others, I leave it up to you. If your geometry is weak, then you better memorize all of them. If you know what you're supposed to know about areas, then you should be fine. Right, the hardest part of calculus is the first 12 years. Another example. Okay, some actual problems here. We are not going to get through all these, and that is okay. Region R is the solid bounded by the graphs of y equals x minus 4, y equals 4 minus x, and x equals 0. Okay, we got to figure out where these things are here. X equals 0, that's an easy one. 4 minus x, that has a negative slope and starts at 4. So I know that's that one. And that other one is x minus 4, so that starts at negative 4 and has a slope of positive 1. So x minus 4. Okay, so now I've got them figured out who's who. Goodness, those points are small, but they intersect at 4. So that's the base area. That's my base. Now, if this could have been a problem on Wednesday's assignment, and we just would have done top minus bottom from 0 to 4, and that would have told us the area. But we're not doing area. We want the volume of a solid whose cross sections perpendicular to the x-axis, so it's a dx problem, are equilateral triangles. So coming up out of the page are equilateral triangles. That's kind of hard to draw since it looks like triangles. So we want to add up all the volumes. We know their thickness is dx because we're perpendicular to the x-axis. We'll go from 0 to 4. And now we just need the area of an equilateral triangle. Because that area times the thickness will give us a volume. So we'll add up all the volumes. 0 to 4. Area of an equilateral triangle. That's the one I said you've got to memorize. That's root 3 over 4 times s squared. Except, what is s? All right, when it comes to drawing these, some people like to try to draw the the picture, like draw the shape coming out of the page. Other people are like, I can't do that. That's just too crazy. And so they'll just draw and label S, and that's good enough usually. Let's see, S would be top minus bottom. So that's 4 minus x minus x minus 4. Please be careful with the parentheses and the minus signs. A bunch of people missed that on the pre-cal test yesterday. And then all of that squared dx. Now, it's kind of up to you. There's cleanup work you could do in there, and that would make typing it into the calculator easier. But the calculator can do all the work as well, so it's kind of up to you. Do you want to push buttons on the calculator, or do you want to do the cleanup work on your own? It doesn't matter. I think for this one, I'm just going to push buttons on the calculator. I guess it doesn't matter, but I'm going to put that root 3 over 4 out front. Math 9, 0 to 4. Again, that means I'm adding up from 0 to 4 all the area times thickness. Oh boy, I got parentheses everywhere. I wonder if it would be easier to clean this up on my own here. This would be negative x minus x is minus 2x. 4 plus 4 is 8. So I changed my mind. I opted to clean it up on my own so that I would have fewer parentheses to deal with. So again, if you don't clean it up, you got to handle all the parentheses. 8 minus 2x squared dx. And so that area is 36.950. For multiple choice test, that probably won't be your answer. What we might should have done is like hold off on the root 3 over 4, because that's what gives me the crazy decimal stuff. So I get 85.333. I can change that into a fraction. 256 over 3. But then I also have root 3 over 4. So 256 divided by 4 is 64 root 3 over 3. Wait, you know what? It's probably easier if it's multiple choice. You're probably just going to get this, and then you're going to take your 4 answer choices and turn them into decimals and see which one matches. That's probably quicker than trying to do that. Yeah, do it that way. So that doesn't take long. Type that into the calculator and see which one matches to your decimal. Number 2, let S be the region bounded by the graph of 1 minus 2x and x squared minus 2. Another one where one's a line, one's a parabola, so it's easy to figure out who's who. I don't really need to label them, but maybe it's helpful. So 1 minus 2x is the top one because that's the line. X squared minus 2 is the parabola. So that region, again, on Wednesday we would have found the area of that region. Today we're going to build something coming up out of that base. A solid has region S as the base and has cross sections perpendicular to the x-axis. So that means their thickness is dx, so it's a dx problem. That are semicircles, diameters in the region S. So that means we've got semicircles coming up out of the page here. Again, I like drawing in the shapes. Other people, they're like, that's too confusing. Just draw in S and go from there. Okay, so I know it's a dx problem. So I'll be going from A to B. I need to figure out where those intersections are. It's very similar to Wednesday. We had to figure out intersections. I mean, it looks like it's -5 to 2 or -5 to 1, but I don't know that that's the best option to go with. Looks like. So I'm going to plug them in and make sure. 1 minus 2x, x squared minus 2. That also means I might be using y1 and y2 later if I don't want to type those in again. Right, there's the line. There's the parabola. Second calc intersect. First curve, second curve. -3. Oh, I couldn't count. I'm glad I checked. I don't want to say I couldn't count. I couldn't read the small numbers. So we'll go from -3. Second calc intersect. First curve, second curve, and now I'll go find the other one. And that one is 1. So from -3 to 1. Next I want to add up all of the little volume pieces. And the little volume pieces are the area of a semicircle times dx. Okay. If you memorize the area of a semicircle, you can use that. If you don't memorize the area of a semicircle, then you can just go with, well, it's 1/2 pi r squared. I know that much. But r, so 1/2 pi r. R is s over 2. Save myself some space here rather than writing out this whole thing again. So s over 2 is 1/2 top minus bottom, because s is the top minus the bottom. So you know what? I'm just going to go 1/2 y1 minus y2 rather than write all that stuff out again. So 1/2 y1 minus y2 squared. Whoops. Make sure you square the right thing. Dx. Again, maybe it's easier to do the pi over 8 thing because then your integral is a little cleaner, and you could put pi over 8 out front, and you just have y1 minus y2 squared dx. So if you memorize it, you can jump straight to here. If you don't memorize it, you eventually get there, but it's a little trickier to get there. So that's one, I don't know. Maybe it is better to memorize that one. Pi over 8 s squared for a semicircle. All right, so back to Math 9. -3 to 1. y1 minus minus y2 square of that dx. Be careful, I intentionally left off the pi over 8 because a lot of times people do that and they forget to multiply by pi over 8. 13.404. Uh-oh, why is that not what the answer choice has? -3 to 1, y1 minus y2 squared times pi over 8. That wouldn't matter. 1 minus 2x, x squared minus 2. Well, it's possible that this person messed it up. Did y'all get 13.404?
I got
4.266?
close.
Because that's what did I do wrong? Or what did somebody do wrong? Back up. Start over. So, pi over 8. Pi over 8 times s squared. So, Math 9. -3 to 1. yeah, it's y1 minus y2 squared dx. Alright, I got the same thing again, so I'm going with 13.404. I don't know what happened on the previous one. And again, the multiple choice is probably going to have that in terms of pi, but you'll just type that in and see if you, oh wait a minute, that's probably not right, because it's 13.404, not 4.266. Yeah, I don't know what happened. Why I'm disagreeing with the preordained notes over here. Number 3. Maybe we'll aim to get through 4. Let's see. Let R be the region bounded by the graph of, I don't know what that looks like. And x squared. Well, I do know what x squared looks like, so I guess that's good. So how am I going to know what e to the negative 0.5x looks like? Graph it. I don't know what it looks like, but my calculator does. So e to the negative 0.5x. You know what? Since I have no idea what that looks like, I'm going to look at that first and then put the parabola on. Okay, I can tell the difference between that and a parabola. Y equals x squared. Okay, that's kind of, I see where the area is. I'm going to zoom in on that and get a better view here. Okay, so there's the region that we're talking about. Oh, part A is a question from Wednesday. Find the area of region R. So that's just top minus bottom from A to B. The trick is I need to figure out what A and B are. So that would be an intersection question. Second calc intersect. First curve, second curve. Go get the first one. Negative 1.429 ... It looks like I'm going to need to use that multiple times, so I'm going to exit and store that as A. Quit. Store as A. Okay, so now I don't have to worry about writing that down anymore. I can always use A. In fact, maybe I can start writing this down. I'm going to go from A to B of, let's see, I already know the F is the top equation. So as soon as I know what B is, I'll be ready to plug into that. Back to the graph. Another intersection. First curve, second curve. Got to scroll over and guess the other one. .816 or .815 ... It doesn't matter all the decimals because I'm going to store it as B, and then I don't have to remember or write down all that stuff every single time. Let's see, this one was Y1, this one was Y2. You don't have to label those, but it might help you keep track of things. So Math 9, from A to B of Y1 minus Y2 dx. .603. So that was a problem from Wednesday. That was an area problem. We just added up all of the little rectangles, top minus bottom times their thickness. Part B, though, says if that region is the base of a solid whose cross sections perpendicular to the x-axis, so that means their thickness is dx, so we'll have a dx problem. that are isosceles right triangles with a leg in region R. Okay, so one of the legs is S. The other leg is also S, because that's what an isosceles right triangle means, whose leg is in the region. So that's 1/2 base times height. 1/2 S squared from A to B. But S is top minus bottom, so I'm going to move the 1/2 out front. A to B. Top one is Y1, or F, minus the bottom one, squared dx. Yes, 1/2 S squared. That's the triangles. Dx is the thickness. So that total is the volume. So we're adding up all the volumes from A to B. So 1/2 A to B, F minus G all squared. Try this again. I'm just going to do a 0.5 out front instead of a 1/2. I mean, that's the same thing. Math 9. We stored A and B, so that's nice. And then Y1 minus Y2. Make sure that's in parentheses so that you square Y1 minus Y2 dx. And so that volume is 0.687. When these show up on free response questions on the AP test, they're almost always like this, where you have the area first, and then you find the volume of some weird shape. Alright, let's do one more. Number 4. Find the volume of the solid whose base is bounded by that circle with square cross-sections perpendicular to the x-axis. Square cross-sections, that's probably our favorite, because what's the area of a square? Side squared. So I'm adding up all of the area times thickness. Area of a cross section is just S squared. This one I can easily see that I'm going from -5 to 5. So that's nice. But I need an expression for S. One way to think of it is top minus bottom, but that's a little bit weird because I don't have, I have a top and I have a bottom, but it's all one equation. Well, I need to solve for y, so let's do that and see what happens. So y squared is 25 minus x squared. What do you have to do when you put the square roots on? Can you square root both sides? Plus or minus, and maybe that's a hint as to what's going on. The top half of the curve is the positive square root of 25 minus x squared. And the bottom half of the curve is negative square root 25 minus x squared. So that's weird. It's one equation to trace out the whole circle, but when it comes to doing top minus bottom, you need an equation with x in it. You need a y equals equation. So solve the equation you've got, and it turns out there's two equations, but you need them both. So S is top minus bottom, square root 25 minus x squared, minus negative square root 25 minus x squared. So that means there's two of them, 25 minus x squared. Alright, negative 5 to 5, 2 square root 25 minus x squared, squared dx. I I guess you could clean that up before you go to the calculator, right? Because the square and the square root would cancel each other out. 2 squared is 4, but who cares? Let the calculator do the work. -5 to 5. Open parentheses. 2 square root 25 minus x squared. Close parentheses. Square all of that. dx. 666.666666666. So 3 decimals, 666.667. That looks like it would be an easy fraction. Sure enough, 2,000 over 3 if we were looking for an exact answer. Either one of those. All right, let's stop there because we have lots of days next week to go. So let's look at worksheet 2, and we don't need to do all of it. Let's try 1 through 5. Worksheet 2, 1 through 5. And then, so on Monday, we'll still do worksheet 2. I'll answer some from 1 through 5, and we'll work kind of together on 6 through however many is left. 6 through 9. So we won't do anything new Monday. We'll stay focused on volumes of cross-sections. And we'll still have 2 days for revolution and then 3 days of review. So we're fine on time. We're not pushing anything on this.